Hello everyone. Welcome to Oracle Groundbreakers APAC Virtual Tour 2020. In today's session on financial fraud detection using graph database, we will show you how organizations can leverage Oracle Property Graph in discovering hidden insights and patterns on financial transactions that are fraudulent in nature or suspicious in nature. Myself, Gautam Pisharam. I'm a cloud specialist, part of Technology Engineering Hub in Oracle. I would like to acknowledge Ryota Yamanaka, who is our product manager for Oracle Graph for the JAPAC region. Our mission statement is to enable or help people see data in new ways, discover insights, and unlock endless possibilities. As it rightly says, in today's session, we will show you how we can leverage Oracle Property Graph to see data or information related to financial transactions in different ways in enabling customers to discover insights on financial transactions and in guiding them to say whether financial transactions are suspicious in nature or fraudulent in nature. Before getting into the actual demo, we would like to show you a few screens from different patterns that can be detected using Oracle Property Graph as a product. So we'll be showing you different screens on different patterns that can be visualized using the graph viz. Let's start with cycles or financial transactions that are cyclic in nature. As we can see in this particular screen, we have financial transactions that originates from the yellow node. It goes to the red node and then it comes back to the yellow node itself. So any financial transaction that originates from one node and it comes back to the same node through multiple nodes is termed as a cyclic financial transaction. Now, it could be even between two accounts maintained by the same person or n accounts maintained by the same person. It could be between different people. We also try to associate the term hops in cyclic transactions. So let's say, for example, if there are uh, 6 transactions involved between different people, wherein the money comes back to the original source itself, then the financial transaction occurred through 6 hops. The importance of cycles is that they are heavily being used to understand the behavioral patterns of customers who make financial transactions that are cyclic in nature, which can then be used for generating recommendations or offers on various bank related transactions. So let's say, for example, um, if there is a continuous inflow between different accounts which are cyclic in nature, there is a chance that they would all be generated a very particular banking offer related to their credit cards or related to their debit cards or related to some of the portals which they use very frequently to make shopping. So cycles holds a lot of importance in coming up with offers or recommendations for different customers related to bank. It could even be thrown um, uh, as a result of the same community to people who share the same interest or the same taste in different communities as well. So it can be spread across different communities. The next pattern is ranking. It's mainly to find account through which most of the money flow. As we can see on the screen, we have one specific account capturing the money from different accounts, and the account who capture a lot of transactions from different accounts in turn transfers the money to a separate account. That's like a pattern. Or we can have a single or a specific individual who is capturing money from different customer accounts altogether. Now they can all be a very important customer, and it's very crucial for banking institutions as well as the financial the fintech companies who try to develop these technologies to offer recommendations or try to make sure the banking services are made better between customers who make the most of the financial services. The next pattern is paths. So let's say, for example, if we have a lot of transactions between a lot of customer accounts or nodes, and what if we find that there are 4 customer accounts associated with most of these transactions, and out of which 2 of the nodes are directly connected? Can we draw a pattern? Yes. So if we try to focus on the nodes 259 and 897, it could be possible that um, indirectly there will be a lot of customer accounts involved in a lot of financial transactions, and 2 of them could be connected, and it would be possible to draw a hidden insight or a hidden path between different customer accounts um, that establish a connection between those 2 accounts. It could be used to discover hidden insight, whether such a transaction could be fraudulent in nature or suspicious in nature. The next pattern that we want to discuss is communities. As we can see on the screen, all the yellow nodes. So let's say, for example, 387, 406, 135. All the yellow nodes are involved in a lot of incoming as well as outgoing transactions. So there is money going from 387 to different IDs. There is money coming back to 387 from different IDs as well. That forms a community. It's a similar case with 406, wherein there is a lot of incoming and outgoing transactions. Same case with ID 135, a lot of incoming as well as outgoing transactions. Now we can also see that there is this little node which connects 387 and 135, which is 916, not 916. We can also see the node 374 connecting 387 and 406. So there are 3 different communities, but in turn connected through different nodes. It's like a hidden insight on whether such a transaction could be suspicious in nature or fraudulent in nature. A very similar screen, we have the nodes 4804, 228, 37, and 133, the green nodes, which are associated with so many incoming and outgoing transactions. But we can also see that node 804 and node 4 are connected through node 158. Now, can we draw a pattern between those 2 nodes using the node 158? So they are all patterns that can be um, discovered like a hidden insight using Oracle property graph by looking into the source data, which would be residing in an Oracle database. In this session, we'll be mostly focusing on how we can make use of financial transactions that are cyclic in nature on both opportunities as well as risk. So there is opportunities associated with cyclic transactions. There is also risks associated with cyclic transactions. We'll be coming to more detail on that. Let's take the 3 main elements of a financial transaction. Obviously, customer comes first. We have the fintech companies trying to leverage the latest technologies to build financial services, which would in turn enable a customer to make use of the various services in different areas of financial transactions. We obviously have the bank who in turn offer different services to the customer. So it's like an ecosystem. It's like a global ecosystem where everyone has to live together in a happy way. And when that happens, the life of a customer is made very easy, wherein customer is socially connected through different apps. He uses various applications in mobile. Um, the fintech companies have tied up with so many other technology or the retail companies or the organizations wherein they'll be able to use the banking gateways and make financial transactions and make the life easy for a customer. A customer uses banking applications and the fintech services almost on a daily basis in almost all the activities related to financial transaction. And when we do that, it sort of establish a trust or the loyalty between all the parties involved. So customer needs the financial services offered by the bank. The fintech companies need customers to make transactions. The bank also need customers to make transactions. Rather than making just one transaction, the bank actually needs customers to interact with different customers, make cyclic transactions or make transactions between different people, which would allow bank to generate recommendations or offers on various services and then throw it back to the customer. So the life becomes very happy for all the parties involved. It's in a very open, good world wherein everything is good. Now, let's say, for example, a very similar transaction. So, if let's say, for example, if multiple people are involved in transaction, what happens when a person has a fraudulent mindset and wants to tweak the behavioral patterns generated by the machine learning modules in the background and then try to get away with either a big loan or with a big offer from a credit card. And that's where detecting the patterns become very important. So let's dive into a quick example. In this example, we can see that we'll start from the right of the screen. So Liam is the customer. He's a person who is the owner of account 2090, who makes a transaction of close to $10,000 to an account 10039, and that particular account makes a transaction close to $1,000 to the account 8021. And then we can see there are two transactions coming from 8021 into the account 1001. And if we notice, we started with a transaction close to $10,000 between account 2090 and 10039. And we can notice that the similar transaction is now getting transferred back from account 1001 to account 2090. Now, it's an example of a cyclic financial transaction. In a real happy world, what would happen when there is continuous inflow of money between different accounts and it's happening across a series of months? There is a high chance they would all be offered different good offers in the banking application or the various mobile retail gateways. And they will be able to just log into the web portal, take a good amount of loan for the financial needs. This happens in a good note. But what happens when a similar financial transaction is leveraged by a person who has a fraudulent mindset? So they can open different accounts using profiles. Either it could be a stolen account or it could be newly created account using fake IDs. They would all be behaving a few months wherein they'll be making financial transactions. They'll be going to an ATM, they'll be withdrawing the money, they will be leveraging the credit card, they would be paying it back on time. They establish the trust and the loyalty with the bank, which will obviously be learned by the machine learning modules in the background. And over a period of time, when they log into the portal, they would all be getting access to quick loans, wherein they can just take it by a single click, going few clicks in few seconds. And they take the huge loan or they try to leverage the services from a credit card, and then they all vanish. So they are all fraudulent in nature, and cyclic patterns detected by Oracle Property Graph can really help customers to discover insights based on the different algorithms that we can run on top of the original data set. From an Oracle Property Graph perspective, let's look at how we can visualize or how a financial transaction is visualized using an Oracle Property Graph. Using the same example, you can see that there is a name of graph which is called as financial transactions. We have vertex or vertices. So account number 2090 is a vertex. Similarly, person is a vertex, company is a vertex. So they are all vertices. Account, person, company, they are all vertices. We also have edge or edges. So owner of is relation between a person and an account. That becomes an edge. Similarly, if you look at the left, we have a transaction between two different accounts. So transaction becomes, coming back to vertex. So we have the label of the vertex. So person is the label of the vertex. And then we also have transaction, which is the label of the edge. We have property of the vertex. So uh, account is the vertex. And then 1001 becomes the property of that vertex. So if you have to look at it from Liam, so Liam is the person name. So Liam becomes the property of the vertex, wherein person is the vertex. We similarly have property of the edge. So if edge is transaction between two different accounts, the actual number that was transferred between those two accounts become the property of the edge. Let's quickly get into a demo wherein we'll showcase both the good part of cycles as well as how that can be leveraged by a fraudulent mindset. Let's first look at the good part of it. So as we can see on the screen, what we infer is that we have a customer with the yellow note. We have an offer which is offered by the bank, which is the red note. We also have different customers in the green notes and different offers in the blue note. The story goes like this. This particular customer has purchased, or this particular customer has leveraged a banking offer, which is the red node. And if we hover over the red node, we can see that it's not just the yellow customer, it's all uh, it's also the green customers who has leveraged that particular offer from the bank. So basically, the yellow customer as well as the green customers have leveraged the same banking offer. And if we hover over the blue notes, we can see that only few of the green customers have leveraged this particular banking offer. And it is the same with all the other banking offer, wherein it's not really leveraged by the yellow customer, but then they are all leveraged by the green customers. Now we can run personalized PageRank algorithm for individual customers, which will learn from the behavioral pattern of different customers. And then it finds out that the yellow customer and the green customer share the similar taste, but yellow customer has not leveraged a lot of the other financial services. They can also be offered based on the page rank so that they calculate the page rank of each of these offers and then throw the best possible offer back to the customer so that the chance of yellow customer trying to leverage that financial service offered by the bank becomes very high. So let's take for example, uh, the blue note that I'm focusing on, it has a page rank of 0.0012. If we look at here, it has a page rank of 0.0013, or we have one more node with 0.0010. Now, they're like the top offers that are recommended to this particular customer with the yellow node because they have all been leveraged by customers who share the same interest like the yellow node. So all the green customers share the same interest or the taste, or it could be friends who are performing cyclic transactions in nature. They could be part of different communities, but sharing the same behavioral pattern, like a shopping pattern. So the machine learning models in the background will be learning from the various behavioral patterns and then can generate recommendation based on the weight associated with both offers as well as the customers. So in this case, we have associated the page rank. It could be a centralized matrix by the name closeness, which would also become very helpful in detecting the similar taste between the customers and then can offer the various financial services to different customers as well. So in a good world, what happens is that um, all these offers will be thrown as recommendations to the banking customer, and it's up to the banking customer to make use of the various financial transactions. Now let's look at a large graph with a lot of financial transactions. Now, how we can find insights? Let's say we look into the cyclic transactions. So we can see that there are a lot of cyclic transactions in a pool of financial transactions. And we can also see that there is a multi-node uh, three-node cycle here between different customers. So it's like a community wherein money has come back to this node 534 after getting originating by the same node, which is 534. Now, this is like a three-node cycle who could be transferring the money between different people over a period of time and then trying to uh, make sure they get offers enabled in the banking application or in a different wallet-based application. And there is a chance they could all log in at one point of the time, and then they could take away different offers or take away a big loan. So we can also try to see if they are all associated with different multiple transactions from the pool of financial transactions. So we are only looking at this particular customer engaged in a financial transaction, which is cyclic in nature between different customer accounts. Now, what if we want to find out if they are also involved in other financial transactions as well, from where we could find um, different other insights as well. So we can click on that particular node and then we can expand that particular customer, which would then fetch the various transactions um, from a pool of financial transactions that are part of the same graph. And we can see that um, it's not just that financial transaction, but they are also involved in um, multiple transactions between different people. So how can we find out like whether some of these transactions are suspicious in nature or if they are fraudulent in nature? So Oracle property graph becomes very helpful in detecting these hidden patterns between different financial transactions. So let's get back into the PowerPoint presentation to proceed further. Okay. So till now, we're looking at a small example on how a customer can leverage the financial services and how the same kind of machine learning module run by the various banking organizations can be tweaked by a person with a fraudulent mindset. So when it comes to the good side of it, we have the personalized page rank algorithm, we have the random walk and the collaborative filtering algorithm. So personalized page rank associates the page rank or the closeness of different customers, and then we will be able to really come up with recommendations or banking financial services offers that can be offered to customers. We have algorithms like a random walk, which is even supplemented by the deep walk algorithm. So random walk basically um, um, uh, try to see if we can recommend different offers to customers based on similar taste or similar pattern. It can also be used to predict the taste of customers based on the behavioral pattern. So random walk can be the output from the random walk can then be used as an input for the deep walk, which then follows the sequence and can be really helpful in trying to predict the offers. We also have the collaborative filtering based on the different closeness. It associates a weight and can then be used in recommendation engines, which would then be leveraged to offer various um, financial services to the customers based on the communities inside or outside of that particular customer network. We're looking at algorithms that can be helpful in the recommendation space wherein it's all good there. But then when it comes to detecting financial transactions that is fraudulent in nature or suspicious in nature, we have the page rank algorithms, which tries to understand the importance of a node connected to a different node. So page rank can really help you identify whether there is an influencer in the network and how the various money inflow can be categorized based on the weight associated with the customer nodes. It can be leveraged by using betweenness algorithm. So betweenness is like if you try to identify uh, two communities. So does the suspicious account belongs to a fraudster, or can we predict that a person with the fraudulent mindset exist or share the connection between two different communities? In this case, the yellow node shares the connection between two different communities. So can we possibly draw a path wherein a fraudster can influence a lot of transactions that are fraudulent in nature in between different communities? We can also have the path analysis. So we can run algorithms like the shortest path or the Dijkstra algorithm or the fattest path. So it's mainly like how quickly or how easily can one node try to influence a different node in conducting a financial transaction that is fraudulent or suspicious in nature. That's where we use these algorithms. Now, revisiting the same slide that we started, we can now see that we were telling about cycles, how they can be used in the recommendation space, wherein they can be used to get offers. But then we also see that cyclic transactions can be simulated by person or set of people with fraudulent mindset, and then they can get away with the money or get away with the financial services, which would then become a burden for the banking organization. It's the same. The pattern of ranking can be used by a fraudulent mindset and can be leveraged in a bad way. All the parts, if there are multi-million financial transactions happening, it's very difficult to draw the patterns between people who makes indirect as well as direct transactions and then try to get away with the money. And similar with the communities, wherein multiple communities are involved, and if we can find out if there is a fraudster who is in turn connecting different communities to influence the financial transactions that are fraudulent in nature. So these patterns can really help the banking organizations to draw a line on finding the hidden insights on the financial transactions that are suspicious in nature. When it comes to the fraud analytics solution, now what we basically do, so banking organizations will have stored the raw data in multiple data source systems. So if we have to look at it from a solution perspective, we can look at this particular cycle as we can, as we have showcased on the screen. We collect the raw data or we collect the needed data from different data sources, which is the step one. We get it to Oracle database, which is step two. So we create the necessary tables in the database and then load the data from the raw data files or by directly connecting to the various data source systems. Once you have the data ready in the database management system, then um, about 12.2 release, Oracle database also has a built-in graph schema, wherein from a traditional relational schema, it can generate very specific vertex tables as well as edge tables, which would still reside within the database. So it's like a graph schema, which is in a graph format. It basically converts the relational data into a graph equivalent in terms of a graph table as well as in terms of a vertex table as well as an edge table. And then once you have the data in the graph schema, you can then load it into the PGX in memory, and it's in the PGX in memory, which we have showcased as step 4, wherein we run the various built-in algorithms. So the algorithms like random walk, deep walk, the personalized page rank, closeness, betweenness, they would all be running in the in memory by having the data loaded from the graph schema. And then that can be visualized in the GraphViz, which is the step 5, which we were seeing in the earlier web browser based visualizations. There are also more ways wherein if I hover over this particular screen, so we can obviously see that the raw data is getting into the database. The database tables are then converted to graph schema and then getting loaded into the PGX memory. But then there is a shortcut also. If you look at database management system, we can use a configuration file which will directly convert the data residing in the traditional database into the in-memory graph data, and then can be visualized using the GraphViz. So for customers who want to keep the data in a graph format always, so that they can also take care of the incremental graph data load in a very structured way, they can go for graph schema. But for data science team who quickly want to load a bulk amount of traditional data into the in-memory and then quickly want to investigate into some critical requirements, they can directly load it into the in-memory by using a configuration file. It could be a JSON file or it could be a Pgql DDL, and then can be loaded into the in-memory. The same algorithms can then be applied and then make sure it's visualized on the GraphViz for detecting the various hidden patterns. All right, so let's look into a few more details. So traditionally, we will have the data stored in Oracle database. So let's take a very simple example. We have a table for accounts with account ID. We also have the transactions, which has captured from where the transaction has originated to which account it has been transferred and the actual amount that was transferred. So they are all traditional database tables. And then we can write a Pgql DDL, which basically creates the vertex table. In our case, the vertex table will have the information on the accounts, with the account ID being the property of the account. And then it will also have the edge table, wherein transactions will be the edge, the source key being from where the money was transferred. The destination key will be the account which received the money, and the actual property, which will become the label of that particular edge. So it's very easy to convert a traditional data which is residing in the database to its equivalent graph format by just writing a DDL query in the Pgql or a JSON file. Again, to highlight on approach 1 versus approach 2, raw data getting loaded into the relational database. From relational database, it gets loaded into the graph schema, wherein we generate the vertex table and the edge table. It gets loaded into the in-memory engine, wherein we can run the various algorithms like the page rank or the random walk, and then can be visualized in the graphs. For data science team, like we highlighted, if there is a critical requirement to quickly load a bulk data from different data source within the database into the in-memory, they can just directly convert the raw data from the database into the graph format using a configuration file, and then it gets loaded to the in-memory, wherein the algorithms can be applied and can be visualized in the GraphViz. Let's quickly get into one more demo, wherein we will show you how to detect various patterns using the built-in query language that we support. It's called Pgql. So we'll show you a few examples on how to write Pgql as well. Let's take this particular example. So I basically generated a very small graph, and I'm mentioning that basically fetch all the graph wherein there is a transfer involved and limited by 10 transactions. So if we count, it's the 5 transactions originating from this particular ID 1 and 5 transactions originating from the ID 2. Now, what if we want to write different Pgql queries. Let's take a few examples. Let's start with a 3-node cycle and still limiting it to 10 transactions or 10 cycles. So I can write a Pgql query in the graph viz on the graph that I have loaded to the in memory, and then I can visualize the Pgql queries on the screen. So here we can see that it has basically generated 10 3-node cycles. So a 3-node cycle, an example is that 673 transferring it to node 8, 8 transferring it to 757, and 757 transferring it back to 673. That becomes a 3-node cycle. So we have taken 10 of those 3-node cycles here. I can also try to visualize it in different ways. I can go to my visualization. I can change it from force to hierarchical. And we can see different 3-node cycles here. So it has basically taken the first 10 cycles from the financial transactions that got loaded into the in memory. What we can also do, let's now try to remove the limit and then fetch all the 3-node cycles and see how big the financial transaction database is. So we are now running a Pgql query against the in memory, wherein the financial transactions got loaded, and we can see that it has generated lots of 3-node cycles. I can see on the screen. Now, how to probably get more insights? They could all be legitimate transactions, but then we can also try to get more insights. Like you can right click on this particular node. So we can see that between 5, 3, 4, there is a list of 3-node cycles involved. There is a transaction between 534, 332, and 297, and then similarly, a lot of nodes above as well. So at any point of time, if we want to find out whether there are more transactions that could be suspicious in nature, we can right click on that particular node and then just click on expand. It would then try to see if that particular customer is also associated with multiple transactions across different nodes. And now we can see that it's not just the 3-node cycle, but then this particular node is basically doing transactions across different nodes, which are not just cyclic in nature, but it could be indirect. And then this can be then used by the organizations to see if it's a hidden insight on finding out a pattern which is suspicious in nature or fraudulent in nature. So let's try to run a different query as well. Let's now try to see if we can fetch the two of the shortest paths from the financial transaction graph that we have loaded to the in memory. So we can see that the system has given back the result of one of the cycle that originates from ID 1, and then it ends at 259, and then it again get transferred back to that particular node ID 1. So the Pgql query basically took the result of the shortest path that originates from the ID 1. So there are two of those shortest path wherein the transfer is involved. Now let's try to see this particular transaction in detail between 1, 259, 387, 867, 38, and 687. So we can now write a query to get information on all the people as well as the edge and the different properties of the edge, wherein there was a transaction between 259 and with the node ID 1. So we can write a Pgql query, and then it would let us visualize that particular result on the screen by giving the node ID. So if we just try to maximize the visual pane, and now we can see that from node ID 1, there has been a transfer to node ID 259. 259 transferred it to 387. 387 transferred it to 867. 867 in turn transferred it to 38. And then ultimately it goes back to that node ID 1, 38 to 687 and 687 to node ID 1. And as a 6-hop cycle, it then again went back to the node ID 259. So this is like a cyclic transaction. Now we can ideally write this. So we can see that the page rank for this particular node is very high. So it could be very possible that this particular node is connected to different multiple nodes and could even be tagged as something suspicious. We were now looking at one of the transaction which was cyclic in nature with a 6-hop. And that's like a shortest path that we discovered based on the last query. Now let's also try to see the different types of financial transactions that this particular uh, person with the node ID is part of. So I can again go back to my Pgql query pane. I can run the Pgql query. So the Pgql query is now hitting the background in-memory engine and then try to load the data from the in-memory engine based on the Pgql query that we have given. So we can see that if we try to fetch all the cycles or all the 6-hop cycles originating from 259, it basically generated so many results. So we can see that the person with the ID 259 is managing a lot of financial transactions, a lot of 6-hop cycles um, uh, within the same financial transaction. Now, this could be very interesting for the banking organization. It would enable them to draw the line to identify the insights whether those financial transactions are suspicious or fraudulent in nature based on the different attributes associated. And that's one reason why we have the various vertices in different sizes. So we have basically interpolated the vertices on the page rank parameter, which will throw the importance of a node in correspondence to the other nodes. And in this case, we can see that the page rank of 259 is very high, which is basically an indication that is involved in multiple transactions that are cyclic in nature. And based on the regulations, you can then throw an alert as well. Now that we have looked at a few of the queries to manage the Pgql, using the built-in visualization, look at how you can actually visualize the same graph by leveraging JavaScript in a custom web application. So what we are looking at here is a web application created by our partner Kaggle based in Japan. It's a very similar concept, and it's trying to connect to the in-memory graph that was loaded into the in-memory. And if you look at here, it's the same node ID with node ID 1. So if I have to run that particular query once again to find the shortest, I'll go back here. I'll run that particular query, which would then retrieve the shortest path. So we can see it starts with 1, the node ID 1, and then it goes to 259, to 387, to 867, to 38, to 687, to 259, and then again back to 1. That's how the story goes. So now if you look at here, we have the node ID 1 here and the various nodes in that particular financial transaction, which was again picked from the similar query. So if we need to find out the cycles involved with node ID 1, we can then click on the cycle, and then we can see that it has generated the cycle here. So we can zoom as well, and we can see that from node ID 1, there has been a transaction to node ID 259, 259 to 387 and 387 from 387 to 867, from 867 to 38, and similarly to 250 to 687, and then it comes back to node ID 1. So we can also leverage custom visualization techniques which are developed in JavaScript as well, or a Java application. And can connect to the in-memory graph server and can fetch the same data that was loaded to the in-memory. The data to the in-memory was ultimately loaded from the graph database or from the relational database, either by leveraging the graph schema or by directly loading it into the in-memory from the traditional data. Having looked at the web application, we'll just again quickly revise on the two ways of loading the data. As we can see, the first screen, the ants carrying the big leaf in a very structured way. The traditional data can be loaded from the database into the graph schema or get converted into the graph schema, wherein they can store the graph data in a very structured way, which can be very useful when it comes to incremental load. And we also have the tiger approach, wherein it's the fastest approach, wherein you can directly convert the data from a relational database, which is traditional nature, into the graph equivalent format using a configuration file, and can directly load into the in-memory in case of a critical investigation coming up. So all in all, these two approaches makes Oracle Graph as a digital ecosystem for the complete graph cycle. It ensure business change. It enable the data scientists to create the graph models in a much quicker and faster way. And it's a comprehensive platform to consume the data very quickly also. You can basically log in into a shell as well to quickly um, shoot Pgql queries, which can give you the results from a shell perspective, or you can connect through the GraphViz. You can connect through the Zeppelin or the Jupyter notebooks. You can also have a custom JavaScript-based web application, which can all connect to the same in-memory data and can visualize or consume the data in different ways. Let's also look at mule detection, which is again part of the fraud detection cycles on how um, Oracle Graph can be leveraged for various mule detection related cases as well. So say for example, if the owner of an account is sharing personal information with others, such kind of a case can be where a customer account can be stolen, and they can then leverage the uh, customer accounts to make financial transactions that could even be cyclic in nature, and then leverage the various financial services. So for mule detection, to find out if different customers are maintaining um, the same personal information. So let's say, for example, on the left, we can see that Alice has an email as well as a telephone, but we can also see that Bob is sharing the same telephone with Alice. So it's basically sharing the same personal information, which could potentially be suspicious as well. Similarly, we have various algorithms like the community label propagation. So how many fraud accounts exist in the same money transfer community? So let's say, for example, on the right, we have the screen wherein um, A01 is making a transfer to A02, and in turn, it's coming back. So if A01 is deemed or declared as a fraudulent account, then there is a chance that the accounts associated with that particular account could also be fraudulent in nature. So these algorithms can be run on top of your in-memory data to identify which all accounts are closely connected or closely associated with a fraud account based on the parameters like page rank as well as closeness. Now, closenesses can also help you identify various details, like if within the community, if there are various nodes with very closeness value, it could be possible that they can all be deemed as forward accounts, especially when they are connected to uh, a customer node with a very high page rank. So mule detection for any use case related mule detection as well, we can leverage property graph. It may not be really fraud detection, but would still be leveraged from coming up with the regulations on setting up the alerts. Like if multiple people are sharing the same personal information, you raise an alert. So we can see the pattern in which how many such customers exist, or in terms of community also, how to quickly find out if there is a influencer between different communities or fraudulent transactions happening between different communities. We can use these techniques as well. Once you run the PageRank algorithm, or in this case, we for feature 3, we have run the personalized PageRank, or for feature 2, to find out how many fraud accounts exist in the same money transfer community, we have run a community serial propagation. Um, Once you run that particular algorithm, we can go into the notebook or the graph shell and then can write the Pgql query, which will give you a visualization as shown in the screens embedded into this particular PowerPoint screen. The importance of mule detection is that it becomes very easy to be detected from a visual perspective. So to give you a very basic demo, we can quickly see that um, there are multiple customer accounts here, multiple bank accounts here, multiple personal information here. So we can see that if you take a look at this particular example, so 202 has an email which is associated with the ID 402, but you can also see that 203 also share the same email. You can also see that 202 has a telephone number, but then 201 also share the same telephone number. So it's like a community of people trying to share information between themselves and then trying to make transactions that are also cyclic in nature. So we can see that 202 who owns this particular account has transferred money to 101 who is owned by 201, and then make a cyclic transaction. So 201 and 202 have the same telephone number, and the accounts maintained by them are making cyclic transactions, and they are also associated with one more ID with a high page rank value as well. So we can see that the page rank associated with the initial transaction is 0.018, um, which stands very high. So we can see that there are multiple transactions getting transferred to that particular account from different accounts, but then we don't have a trace. So it could be an indication that they are getting transferred from an account which is outside of the same bank. It could be a different bank altogether. Now, how can you draw some suspicious pattern based on that? How can you further investigate into the detail? So graph helps you visualize this information as well in relation to running the various algorithms in the background. Again, to stretch on where we can pick this up. So we have been looking at how Oracle database can be leveraged, and how we can load the data into the in-memory, and how we can run certain page rank or community detection related algorithms on top of it. Now, ultimately, Oracle database also has the machine learning capabilities or the advanced analytics capabilities. So what in turn can we do? Based on the data set that we have generated, even with respect to the vertex table or the edge table, we can run these algorithms and then have the results captured in the database, which can then be used for prediction. So say for example, some details like name, age, occupation, branch, balance. So based on the various financial transactions with different properties involved, we can then try to run certain algorithms on top of it, like let's say collaborative filtering, which would associate the different closeness values and then give the output in a table format, which can then be captured into uh, a different table, and they can be used from a machine learning perspective. So we would have one base data table with the raw information, and based on the algorithms that we run on above, we capture that result into a different table, and then can run advanced analytics on top of it by leveraging the built-in machine learning modules of the database, and can uh, uh, generate the prediction rate whether they are a fraudulent transaction or a non-fraudulent transaction based on the behavioral patterns that are learned by running the algorithms on top of it. So we can also club in machine learning with an Oracle database related graph system, and ultimately be able to predict whether transactions are going to be fraudulent in nature or not. Um, how is Oracle Graph different? Oracle Graph has been proven to run with billions of edges with highly scalable graph databases and the performance limits as well. It's very easy to write the queries to run algorithms on top of your massive financial transaction data set and then visualize it on screen using the graph. It also becomes very easy and accurate to detect the cycles. So again, to reiterate, to be able to detect fraudulent transactions, it's very vital to run these algorithms on top of your massive data set, and being able to fetch the cycles in a very easy and accurate manner. Let's say, for example, we are trying to deal with billions of transactions, and we have to fetch the cycles from those billions of transactions. So it has to be very accurate. It has to be very easy as well. It obviously has to be scaled in a very efficient way so that the performance is not impacted. You're still expecting to get the results back in few minutes, even from billions of transactions. So Oracle has been proven to be that scalable to work with a huge data set. We also have the built-in graph algorithms and the graph visualizations, and altogether with the combination of all this, it can be consumed or leveraged by people of different um, skill sets. Let's say data scientists or the data professionals, the developer, the business analyst, the business executive, the compliance from a compliance perspective as well. These models can be consumed by different people from different platforms. They can leverage the shell, they can leverage the graph visualization, they can leverage the notebooks, they can leverage the custom application, or they can also have the Java applications written. So there are different ways to consume the graph data that we uh, leverage from the Oracle database as well as from the in-memory, which ultimately help banking institutions to discover insights on financial transactions that are fraudulent or suspicious in nature. I hope that was an interesting session on fraud detection using graph database. Thanks for listening. Thank you.